This lecture concerns the fundamental theorem of calculus. Now, I think this is the big deal, and I'm going to present it in a version that I think is how it's developed, how it was used. Now, let's understand this. In all of calculus, this one result, this one theorem is called the fundamental theorem of calculus. It's not called, oh, it's just an auxiliary result, or it's something out there, or old Isaac said this. This is the fundamental theorem of calculus. Again, you have all these tools in your toolbox. This is the one, this is the key result. This is it. For differential calculus, I think the global optimization theorem is the big one. This is by far this is it. This is the guy. This is it, the main one. All right, so again, I want to put this into context. What we're dealing with is solving the initial value problem. Now, again, this is the topic that was on everybody's mind. We had force equals mass times acceleration, which is essentially conservation of momentum. So what we had was, again, think of really one derivative this time, as I said. So the derivative of velocity is force over mass. So our goal, we knew the force and the mass of the object. We want to find the velocity. Given the velocity, we have the derivative with respect to time of position is velocity. We knew where the projectile went, right? We knew where we're shooting, right? Trying to bombard the French with our cannons, right? This is it. This is it. So this is the prototype of conservation, mass momentum, and energy. This is it. This is the basic, simplest form of that problem. I'm given the derivative. I'm given the dynamics. I'm given the initial position of the cannon. I want to know how the shell is being fired, right? So this is the initial value problem. Okay, so this is it. This is what we do. This is the main thing we do. Again, I'm not saying you don't use the other theorems. Global optimization, closing bounded intervals, that does come up. But this is it. This is what you're going to see. All right. The problem is anti-differentiation, relying on the differentiation rules, never works. I mean, it rarely works. In the scheme of problems, right, you're never going to be able to solve it using these integration rules. I mean, you're just never going to. You have two approaches. You can replace your derivative here with a Taylor series, a Taylor polynomial. And of course, you can integrate a polynomial. That's one strategy. Or you can solve it as we're going to learn here. The differentiation rules rarely, in fact, never, if you're solving a problem like that, it's just a prototype. It's just a baby problem. I mean, I don't care. Jump through hoops. That's what you're doing. So that's the problem. So what do? You throw your hands up and you give up? No. I mean, you're Newton, you're Leibniz. You sit down and you figure out how it works. Now, we're going to go through the process, and it's just simply brilliant. If you want to become a great writer, what do? You read the great books and try to understand the great books of literature. You want to become a great artist. You go study the techniques of the greatest painters of all time. You want to become a great musician. Again, similarly, you go look and study the greatest composers of all time and their scores. You want to be a great scientist, engineer, mathematician, economist. This is it. Let's see how Newton did it and how you should learn to think. This is simply magnificent, all right? So what the fundamental theorem of calculus is going to do, it's going to tell us, right, this is our problem. This is the prototype, conservation of momentum, right, force equals mass times acceleration. Fundamental theorem is going to answer the questions for us. It's going to tell us there exists a solution. When there exists a unique solution to this problem. I mean, if you're going to solve a problem, you want to know there's a solution. When you put down the weather problems, right, solve for the weather equations, you'd like to know there's an answer. In fact, for the weather equations, you don't know. You just have to go along and hope. But you'd like to know. That's ideal. The ideal case is you'd like to know there exists a solution, a unique solution. Reality is one solution. And I'd like to know how to compute that solution, or at least an approximation to that solution. This is actually called approximation solvability, constructive approximation. So I don't want to just know there's a solution. I want more. I want to know how to compute that solution, or at least an approximation to that solution. This is what we want. This is when you work in the field, when you work on real problems, real world problems, this is what you want, right? This is the game. This is the game. Here's an example. Here's an example. I'm going to take a problem that's differentiable on the interior, right? And it's continuous including the ends, right? Satisfying, this is the dynamics. This is the dynamics. Actually, I should have it just continuous, not include the 1, because I'm only going to go up to the 1 here. And I'm going to say, so this is my dynamics. This is the initial value problem. This is my differential equation, my ordinary differential equation. And you can see, and this is my initial condition. So I'm telling you, I want to find a function, right, whose derivative is this, who satisfies this initial condition. Now this is an easy one, right? This is an easy. So let's start with an easy one, right? Let's start with an easy. They can make this anything you want. And the thing that's so interesting about this is, this is not 1890. You give me almost any function here, I can plug it into Excel using this technique and solve it in 30 seconds. Every initial value problem, then I drew the graph. I said you can do it by Taylor series or the fundamental solution approach. That's how I solved it. I solved for the derivative of, right, the equation, so I actually solved for the derivative equaled something, had an initial condition, and I used a technique here to do it. And you can do it in 30 seconds. I mean, this is so efficient today that to do the techniques, in my opinion, that you're going to learn in your engineering math course or the ODEs, that's the extreme. That is so extreme that may come up. It may be important, but that's the extreme case. This is how we actually solve it. And for one variable, it's nothing. It's trivial. And it's completely general. So let's look at what's going on here. In terms of the notation, my derivative, fx, is 3x plus 3. It's the right-hand side. And my initial condition in my notation, f0, right, because the initial time is 0, is 0. Right? That's in terms of my notation. So what do I have? What data did they give me? They gave me a point. They told me when time is 0, again, in one derivative it's really time, I'm just keeping the x's. Time is 0, and the state of the system is 0. Now again, in a multivariable setting, you might be looking at the energy profile or in a room. So you would have temperature, pressure, density. You would have more variables. You would have the XYZ and time. So they're more involved there. But this is the prototype. This is my initial state of the system. At time 0, the state of the system is 0. Right? And that's given in the problem right here with the initial condition. That gives me the point. And what else? Right? So that's the point. That's what this initial value, initial data says in terms of my point. Right? When you see the initial data, you should be thinking this. Okay, what else do we have? I have the dynamics. In other words, this isn't just any old function. This is the derivative of the solution function. This is the thing. They gave me the derivative. They just handed it to me. I don't even have to work for it. They handed me the derivative. Now, you might have to measure this in the lab, the force right over the mass, but this is given to me. Now, notice, at a particular point, right, not just generically, at a particular point, this derivative is 3. This is, in fact, the slope of the tangent line, right? For example, it's 0. Now this function, now I'm only taking this derivative greater than 0, but okay, let's say 0, right? This derivative equals 3. The slope of the tangent line at this point is 3, right? That's what it tells you, right? That's what it tells you. The slope of this tangent line is 3. Okay, what do you have when I tell you about a point and a slope? What should you automatically be thinking of? A tangent line, a linear approximation. I don't know the function. Again, I understand if you've been training yourself. I don't know the function, right? I don't know the function, but I know a point and I know a slope, so I have a linear approximation. And we know that there is a neighborhood such that the linear approximation is basically exactly the same as the function. There's some error, but again, how accurate do you need? 20 decimal points? I mean, 4 decimal points? How accurate do you need it to be? So there's a neighborhood where you're as accurate as many decimal places as you want. Right? Point, slope, light bulb, right? Light bulb, you've got the tangent line, you've got the linear approximation. So point, slope, tangent line, linear approximation. Now, I don't know what the function is. In fact, I do, right? We know we can do. I don't know what the function is, but it's going to be very close to this in some neighborhood, right? It's going to be very close in some neighborhood. So, what are you going to do? Suppose you want to, okay, you say this is the approximation from 0 to 1. I can do better than this. I can do better. So anyhow, this is my linear approximation. I'm going to call it L0, right? The 0 is going to mean it's based on x equals 0 to start with, right? And that's 3x. And that's 3x. All right? So what can I do with this? I can predict what the function is going to be. I don't have to go the whole way. Remember, the linear approximation is good in a neighborhood. I can use it to predict the value of the function, right, when x is 1/3. Now, it's not going to be exact. You know, the closer this point is to 0, the more accurate it's going to be, right? The linear approximation is good in a neighborhood. The smaller that neighborhood is, the more accurate it's going to be. So I can make it closer, but let's just say 1/3, because I'm doing this by hand, right? On a computer, I'd go to, as small as I want. But let's say 1/3. Now, what's the value of the function at 1/3? I don't know. But I do know it's going to be very close to this linear approximation at 1/3. It's going to be very close in this particular case to 1. So now I have another point. For all intent and purposes, this is exact. Okay, maybe there's 8 decimal places of error. Forget it. This is exact. This is what I need an answer, right? I'm not going to sit around and philosophize and this and I need an answer. You're in science engineering. You need answers, right? You're in the applied. I need an answer. This is close. Maybe that's not exact, but again, how accurate do you have to need it? If you want it to be more accurate, instead of going to 1/3, go to 1/6. I mean, I don't know what to tell you. Go to 1 whatever. Keep cutting it in half. So this is good. For all intent and purposes, this is the exact answer. How do I make it go forward? Well, restart the problem here. Take this to be now your new initial point. So at this point, notice I have a point, right? I have a state, right? It's maybe not exact, but for all intended purposes, it is. And remember, I gave you the derivative. I gave it to you. I'm handing you the slope of the tangent line anywhere you want. For free. I'm just handing it to you. So the slope, change in y, change in x, when x is 1/3, at this point, is 4. Point, slope. Draw yourself another linear approximation. Y equals mx plus b. There's your slope is 4. Plug it in, get your linear approximation. So I'm staying here, right? Most functions are piecewise. I've said that. This is the reason why. Here, this is what I look like. And now once I hit 1/3, I'm going to change and go up this way, change my trajectory. Right? So again, the function is very close to the linear approximation if the neighborhood is small enough. So for all intent and purposes, I have the function at when x is 2/3. Now, of course, it's not exact. The wobbly equal sign means approximately equal to. It's not exact. But again, if I want it to be exact, I'll just, instead of going to 2/3, go to 1/3 plus some little crumb of a number. So for all intent and purposes, this is the value of the function. This is where the function is when x is 2/3. The value of the function is 2 1/3. Forget that I actually don't know the function. I have it here. This is it. Plus or minus some crumb error, this is what I have. And if I want it more accurate, just make the neighborhood smaller. Go from 1/3 to some little piece over here. Fine. So I have a point here. Remember, I'm trying to get to 1. Just repeat. Repeat. Once more, repeat. So now I had the point here. Again, I'm given the tangent line anywhere I want. Anywhere I want. And okay, so at that point, the slope of the tangent line is 5. You plug in and you get your next linear approximation. Right? Your next linear approximation. I mean, this is amazing. F of 1 then is about what the linear approximation is. So I'm not just taking one linear approximation along the way. I keep correcting it. I'm stepping. This is called time stepping, time marching, a time marching scheme. This is what I think Newton did, because this is what I do, and I'm a descendant in that realm. That's the kind of thing I do okay, up. But Newton started it, and it's brilliant. You just sit down and look at the tools you had, right? Replace the function by its linear approximation. Come up with what the tangent line means. That's where the limits come in, right? Come up with it. What does it mean to have a tangent line? How would you define the derivative of a tangent line? That's where this journey started. But I don't think Newton, I'm guessing, I don't know, but I'm guessing, I don't think Newton started with that. That was a tool that was developed later, right? What Newton was looking at is this kind of a picture, I believe. Then you came up with the concept of how you define a tangent line instead of guessing. That leads you to the limit. That gives you the slope of the tangent line, right? So you're not guessing. Then you realize the linear approximation is a good bet. What's the next best thing? Well, okay, it'll go so far, then do another linear approximation and another one. That, I think, is the idea. We're time marching here. And I mean, that's simply brilliant. Today with like Excel spreadsheets, you can solve anything. You can solve anything. In literally a minute, I can plug this in, get Excel to compute these and have a picture. And again, that's how I generated all the pictures. In implicit differentiation. Or, of course, you could use the higher order Taylor polynomials and other things to approximate if you had all those derivatives. But notice my function here only has one derivative, so I can't use the Taylor series idea. All right, so I have the linear approximation, the third one, and so anti-differentiation is finding the function when we're given fx. This is the general idea, anti-differentiation. Well, let's look what we have. We almost have f, right? Almost. Here's the exact answer. Of course, you don't really know this yet, but if you integrated it, you get this. We'll do this later. Here's my linear approximation. Okay, it's piecewise, right? It's piecewise, right? It's a line on each piece of the domain. Look at the picture. Look at the picture. This is the actual solution. This is my very crude approximation. I took 1, 2, 3 steps. Maybe if you have to do it by hand, maybe if it's 1890, this is what you do. But I mean, I have a computer today. I have a PC now that has the power. I could go, instead of from 0 to 1/3, if I want it more accurate, I take a smaller neighborhood. Go from 0 to 0.1. Go from 0 to 0.1 to 0.2, 0.3. Go from 0 to 0.001. You can make this as accurate as you would like it so that you cannot distinguish the difference between this red line and the black linear approximation. Who cares if it's given like this? I have a computer, right? I mean, I have a computer. It's not like, again, the 17th century. And this is it. So for all intended purposes, I'm simply going to use the linear approximation. I can set up for a function of one variable. I can set this up and do it on a computer in a minute, no matter what problem you give me. And that's it. Now, there are more advanced ways to do it. There are ways to do it with problems that have particular issues. That's fine. But in one variable is... Functions in one variable is so easy, you don't even need really the advanced techniques. It's just so easy unless something really extreme happens. So I just connect the pieces I want, and it's a very good approximation. And the idea is so straightforward and simple, right? And we approximate the derivative now by, so here's the derivative we were given by the derivative of the linear approximation. Here's our derivative, right? It's piecewise. It's not as smooth. When you take the derivative, it doesn't smooth things out. Look at this. Now, you say it looks bad. You say it looks bad, but you see this all the time. This is pixels. This is pixels. I'm going from 0 to 1/3, 1/3 to 2/3, 2/3 to 1. If I went from 0 to, again, 0.01, you could have all these little lines here, and you couldn't even distinguish it from this. This is what you look at your monitor, right? Your screen on your phone, your tablet, your PC. This is it. On each pixel, there's a number that corresponds to a color. That's this, right? What's the difference between 4K, 8K TV? This. I just take smaller piecewise approximations. This is how we do it. This is reality. And in one spatial variable, this is not hard to do. Now, if you're doing the weather equations, you need the world's biggest supercomputers. But this is one variable, right? One variable. So, I mean, this is it. And it's so easy to do. And I wish we had time in the labs, in the class, to actually explore this, because this is the game. So let's summarize. Here's my function. Here's my approximation. Here's my derivative. And here's my digitized version, basically, of the derivative in the function. This is it. Now, hold on to this idea, though. We're going to see later on these piecewise constant things. And we see it's actually not too bad as long as you don't jump big steps, right? So if your function itself is linear, keep in mind its derivative is piecewise. And this is going to be the key when we talk about, like I said, when you have the highest derivative is 1, when you have your highest derivative is the first derivative, it's a time variable. If your highest derivative is 2, it's a spatial variable. And we're going to see how you handle spatial variables by handling this. Okay, so you just hold on to that idea. I mean, this is everything. This is everything. This is the key. This is the shooting match. All right? So, I mean, let's look at this graphically. Now, remember what we said with Newton's theorem. And I don't think Newton did the second part. I think Newton did the tangent line piece up till now. But again, what you were promised is there exists a function, or at least how to calculate that function, right? That satisfies the initial value problem. So I didn't give you the function. I mean, right? I gave you this linear approximation, but that's not saying this isn't a function. I told you how to calculate this, but let's convert it to a function. Now look at this. Look what we have. Here's a linear approximation. Here's its derivative. Check this out, right? Look at this. Again, how do you figure these things out? I don't think you figure these things out by sitting there under a tree waiting for the apple to fall on your head. Look at it. Stare at the pictures. Do the most obvious things you can do. Do the most obvious things you can do. If I have a linear approximation, slope, right? This was the y equals, right? This is the slope m, x plus b on this side, right, to start with. How do you interpret this? This is the linear approximation, right? L at 1/3, the linear approximation of a third, equals the linear approximation. This is your b, right? This is your slope, so it's going to be x minus 0, right? So this is your linear approximation. Stare at this for a while. What does it tell you in terms of the pictures? This is this distance. This is this distance, right? This is this distance. What's this piece? Look what this is in terms of your derivative. Remember, the derivative relates to the function, right? This is the antiderivative of this. This is your base, and this is the height. So what is this quantity? What does this change? It's the area here. It's the area under your derivative here. I mean, that's remarkable. You're relating the derivative to the function. The derivative to you're anti-differentiating. I can tell you what the change is here just by looking at the derivative here. The area here, again, I'm digitalizing. I mean, it's simply brilliant. The area here gives me the change here. Look at the next piece, right? So this point here is the area, plus where we started with, in this case 0, in this case 0. So that gives me this point. Let's continue. Let's continue. Again, you don't solve problems, at least in my experience, by going out all crazy. You start with the simplest problem in the simplest way, and then you keep advancing. So if I'm going to have time and space, I'm going to start with the simplest problem. I'm not going to jump into the most crazy high-tech version. That's the mistake we make. We jump in and try to figure out how it works in the crazy. Understand the basics, but get here how to think. Look how simple this is. Of course, it's brilliant the first time. But, I mean, you look at it and you just, my God, look at this, right? So it's the area plus your initial jumping off point, right? Your initial jumping off point here was 0. So it's this distance, right? And it's just this area. Let's look at the next one. Oh, and so I want to put this in. In a notation of numerical methods, the mesh is these points. So you'll hear people talk about the mesh. In higher dimensions, you have more. We'll talk about that later. But this is your mesh, and this is your mesh size. We call it h. I don't know where h comes from, but we call it h. So, okay, this is my mesh size, and this set of these points is actually called the mesh. You'll hear people talk about that. So I can get a more accurate solution, right? A smaller neighborhood by taking a smaller mesh size, right? So go from 0 to 0.1 to 0.2, 0.3. The mesh size is smaller. The mesh is larger. So these concepts you will hear people talk about, right? So again, this is remarkable. The slope of the tangent line gives you the height, and the mesh size gives you the base. I mean, it's simply amazing. So how do I get my next point? Same argument. The change from the initial one to my next point is the linear approximation of the linear approximation of 2/3 minus the linear approximation at 1/3. That gives me this height. And that's going to equal the area on the next rectangle, right? Base times height. So my height is 4. Notice the width, 2/3 minus 1/3, the mesh size here, plus where I was to begin with. And that's it. That's my next point. I mean, really, you're interpreting the area under the derivative, okay, the digital version of the derivative, right? And that tells me it relates to the function. Anti-differentiation, right? I'm relating the derivative to the function, right? Anti-differentiation. And we can continue again, right? So I start here and I want to go to here. This distance is this area, right? This area. I know what it is. Remember, I always get this number. You gave me the derivative. With the derivative evaluated at a point, x equals 2/3, right? It gives me this height. And this is the difference against the mesh size. This is the value I had previously. It's 4. I mean, it's amazing. Now let's see how we can put this all together. And again, I don't really think this is what Newton did. I think Newton came up with the tangent line, this idea. I think this came later. I don't want to get into the whole math history thing. I don't know. I'm not that interested. Maybe I should not, whatever. I want to construct solutions. Okay? And then also, again, no reason to stop at 3 rectangles. You could have as many as you want, right? As many as you want to make it more accurate. I mean, eventually you learn in numerical methods, you can only go so accurate because the computer can only resolve things so accurately, but whatever. So, okay, I need a better notation, right? Let's clean this up and let's see where this train goes. So L1, right, just what I had before. It's this slope, the change in x, right? This is the area plus L at 2/3. Right? That's what it was. But notice, L at 2/3 had its own little formula, right? An area plus L of 1/3, right? An area plus L at 1/3. Okay, I mean, let's keep going. L at 1/3 had its own little formula, area, right? Base times height plus where we started from. Okay, so far so good. Now this is a little cumbersome because you're dealing with this notation, but this is the derivative, right? Fx evaluated at 2/3, fx evaluated at 1/3. Right? So let's replace this with this, because this is what's given in the problem is why I like this, right? I'm given this function in the problem. And then this one is replaced with this. Now again, I'm not asking you to do this. What I'm saying is appreciate the process, right? You want to be great. Appreciate how it's done, right? This is replaced by this, right? The derivative at 0. The slope of the tangent line at x equals 0 is fx evaluated at 0 and L0. Okay, now you say, well, where does this go? well, I want to use a notation here. I want to clean this up. It's cumbersome. I mean, you can imagine having 100 points in your grid. This is cumbersome. It's just cumbersome. There's nothing wrong with it. It's just you could do dot, dot, dot or something, but it's cumbersome. I'm going to use a shorthand notation. Now, before you have heart palpitations, just listen to me a second. Just listen to me. This notation is so natural, right? You're looking at this and you say, oh, I hated this. Oh, I don't understand it. But it's so easy. It's so easy. This is a sigma, right? Sigma. Sigma is Greek for S, and S stands for sum. I mean, what else? You can come up with any notation you want. Try. Could you come up with a better one? I'm summing up 3 terms. 1, 2, 3 terms, right? I'm summing them. You could call it an S. I mean, you could call it an S. But the sigma looks pretty slick, right? I mean, you got it. It looks pretty good there, right? It looks pretty good there. So sigma is Greek for S, and S stands for sum. Notice I'm starting at 0. You could start at 1, right? You could go. There are 3 rectangles, so you could go 1, 2, 3, right? First rectangle, second rectangle, third rectangle. It's the same. You just change the notation a little bit. But notice when I is 0, I get 0 over 3, which is 0. When I is 1, you get 1 over 3. And when I is 2, you get 2 over 3. I mean, how nice. What a succinct way to write that. Now again, for 3, I don't care. I don't use this. I don't do it. But again, if you had 100 of them, do you want to write that all by hand? This meets that. And this just gives you that. It's just notation. That's all it is, right? So the sigma is Greek for S. I start at the 0 or at the first rectangle here. And I end at, well, the second 2/3, or really 1 to 3 would be the first rectangle to the third rectangle, or the 0th point to the second point, right? There's 3 points in the grid, or 4 points, or 3 points in the grid, right? 0, 1/3, 2/3, 3/3. So I start at 0 point and I end calculating with the second point. So again, it's just how you want to interpret it. But the notation just means sum. So this is called the third Riemann sum. Presumably Riemann was the guy that did this. I don't think Newton took this approach, and you'll see where this goes. This is the third Riemann sum, and we call it, I don't know, S, right? S3, 3 rectangles, sum of 3 rectangles. And again, you could have more rectangles. And you see, in principle, that as I take more rectangles, the answers get more accurate, right? The function gets to be a better approximation, right? It's all about approximations. As I take more rectangles, why? Because I'm using the linear approximation to approximate the function on a smaller neighborhood, right? Recall that. On a smaller neighborhood, more accurate. So in the limit, right, what's the answer? If I have Riemann sums and I take, well, n gets large, again, infinite isn't a number. It just means keep taking more and more and more, right? The limit is I take more. So I look at 10 rectangles, 100 rectangles, 1,000 rectangles, 10,000 rectangles. You'll see eventually the answer stops changing. But that's what you're doing when you say n goes to infinity. I'm looking at what happens when I have more and more, the trend of rectangles. So if I take the limit on this side, I get Sn, right? There's 3 of them here. And on this side, well, the limit is n goes infinity. I still have limit 1. What's going to happen is this is going to approach the actual value of the function. This is my initial value, right? It always has been, right? And this. Now, again, you can make this precise. The book does proofs, probably you see this stuff, but I'm not going to focus on that. That's what a mathematician would focus on. Does this become that? You have to estimate things. It's fine. But conceptually, you can see, as I get more and more rectangles, more and more accurate on the tangent line, the result at the end becomes exactly the same as the value of the function. And so I need it to be the limit of these sums. Now again, let's keep exploring this. Let's explore this. So the idea is so simple, right? I mean, I'm not saying you could figure it out. I'm not saying I can figure it out. I hope I can figure it out. In my own work, I hope I've done such certain things. Okay, but this is the goal, right? You're looking into the minds of the greats, the ones that have survived because their work was meaningful, not the charlatans, not the jokers, who's your daddy got me there, right? This is the guy that did it. Right? And this is my solution to the initial value problem. If I can find this for any value, that's what I'm looking for the initial value problem. Okay, now let's start looking at this in better notation. But this is the fundamental theorem of calculus. This, the way of calculating it, either by the tangent line approach, which is how you work with time problems, or the area under the curve, which is how you work for spatial problems. This is how you calculate that solution. Now, look at it. This is the limit, right? Remember what we're looking for. This limit gives you this difference. So if I know this, throw it on this side and I can figure out f of 1. So this limit is the end. This gives you this gives you the answer. I need a notation for it. Okay, I could call this limit number, happy face, Ivy plan, Lakers, right? I mean, you could call it anything you want. They're not helpful. They're not helpful. I picked this notation. Now, why did I pick that? Again, don't stress out. It's exactly, let's look at why we pick it. It makes perfect sense. Where, remember, this sum is the sum starting at the 0 grid point to the second to the last grid point of the slope of the tangent lines times the width, right? Base times height, sum up all your rectangles. That's what this says. That's how you read, that's how I read this. And this is called the nth Riemann sum because Riemann was presumably the guy that came up with this, right? So, okay, this limit is a number, and this number is, well, this difference. It's the answer at the weather tomorrow, given the weather today. That's what this is. This is real. This is how we do this. Now, okay, let's look at this notation and see, where does this come from? It's stress. This is one complete symbol. There's not this piece, this piece, this piece. They're different. This is one chunk of a symbol. It all works together. Again, you could call it Q. Well, what does that mean? You could call it smiley face. Where did this come from? Now, of course, I was not there. But again, using common sense, you can figure this out. This is called the definite integral, this number, right? Again, it's a number. It's like calling it the slope of the tangent line. It's a number. We gave it the symbol dy dx at x equals a, right? We gave it a specific symbol. There's no dy dx. It's just a chunk of a symbol. This is exactly the same thing, and it's called a definite integral. It's definite because it equals a number. All right, it equals a number. It's the definite integral. So there's no ambiguity about it. This is a number. For example, the indefinite integral is going to be a set of antiderivatives. What's definite about that? You have to pick the one out of there you want. This one is definite. It equals the number, and that number is the limit of this. Now let's see where this symbol came from. Again, it's one chunk of a symbol. It's one chunk of a symbol. Well, let's see where it came from. The integral sign is a sigma. Look, take a piece of paper and write this out 100 times quickly. And you know what's going to happen? It's going to wind up looking like that. I mean, do it. I've worked problems out. I wrote this out. This is where it kind of occurred to me. I wrote this out over and over again, and you get sloppy. And what happens? This turns into this. I mean, you come up with your own reason. That's what I'm sure it came from. Because this is the kind of thing I do. This mushes into that. Okay, so the integral sign is a sigma. It stands for I'm summing things up. I'm summing things up. I'm starting at the bottom. The bottom here is alpha, all right? I'm starting at the beginning, say 0. I'm going from 0 to 1. I'm starting at the bottom at 0, and I'm going, and I'm going to the top 1. I'm going to the top, the second to the last grid point in this case. I mean, how else? You can come up with a better notation. But this has survived because people thought it worked well. I mean, again, you can do what you like. Notice fx is the same. This is the digital version of that point. Right? This is put in 0. This would be 0 over whatever it is, whatever the n is. It's 0. That would be maybe your original point. So again, you can adjust this, but this is the digital version of your first point. And so this is the derivative evaluated at that point. So this is the slope of the tangent line there, the height of the rectangle. And well, dx is just the limit version of delta x, right? This is the discrete version, right? This is the difference, and we use the notation. We did it with derivatives too, dx, dy over dx, okay? They didn't have a meaning. It's just delta y over delta x turned to dy dx. Same thing here. This dx here. I mean, this dx doesn't stand on its own. This dx doesn't mean anything. It's just this chunk of a symbol. This is one stamp, means this number, which is calculated in this way. So I'm summing from the bottom to the top, from 0 to 1, alpha to beta, right? Base times height. That's what you're supposed to think about when you see this, right? When you see dy dx at x equals a point, that's what you think. Change in y, change in x, slope. Slope of the tangent line at that point. When you see this symbol, this number, it's the base times the height, summed, right, between here and here, a bunch of rectangles. That's what you're supposed to think. I think it's pretty clever, right? I think it's pretty clever. And in fact, you can prove that if a function is continuous on the interior, right, so this is my derivative, this is my dynamics, continuous on the interior, and it's bounded. It's bounded for any choice of any point inside here. So it's continuous and it's bounded everywhere. Then the limit of the Riemann sums exists. So that limit exists. So the definite integral exists. And that means that f of x, this function here, is integrable on this integral. And we write then that this function is the antiderivative, right? This function is in this class, in this set of functions that are integrable. So this function has an antiderivative. That's what this says. This function here has an antiderivative. How to compute it? We just did it. We just did it digitally. And I said that that limit exists. So that's it. That's it. You can do it at any point. Now, the beauty of this is really general. Really general. Now, again, we were talking about regularity and smoothness. The derivative is smoother than just being continuous. The second derivative is smoother than being one derivative. But that's not the issue. This kind of function, this is not smooth. This is where the action happens, right? This is the shock wave, right? This is the fracture. This is where something important happens. Like I said, we're not going to calculate the room temperature in the classroom. It's 70, right? Nothing happens. I am interested in where I have a shock wave. I am interested in where a fraction happens. I am interested in where something big is happening, something breaks, right? The economy's going along and then a shock happens here. Something changed, right? We imposed a tax. Something happens right here. That's what I care about. And notice an integral formulation can handle that. What this says, and this is okay, it's not the end of the world. It just says I integrate from here to midway, and then I integrate from the break to the end. That's what it says. Just break the one instead of going directly over. I do sums under this first piece, right? And then I do sums under the second piece. Bingo, done. And this gives me the ability to describe these kind of phenomenon. And we'll see how we integrate that on my very last lecture. All right, that's what integration by parts does. This is a big deal. The integration gives us a framework for handling these kinds of events that we find important. Okay, so we'll look at this. So again, we know functions are integrable, and what we get from the Riemann sums we can summarize like this. Now, people think this is the fundamental theorem of calculus. I don't think so at all. I mean, I think it's a consequence of the fundamental theorem of calculus. But why would you call this the fundamental theorem of calculus? I mean, in all of calculus, if you have to know one idea, this is it. I mean, no way. I'm telling you how you can solve these conservation equations, these time dynamics, for any function out there. That's what I'm telling you. I'm telling you how to solve the prototype conservation of momentum equation, force equals mass times acceleration. That's how I'm telling you how you can calculate that. Go to Excel, write it in, and any of these problems you can knock out in a minute, right? That's what I'm telling you. Or you're telling me this, whatever is the fundamental theorem? No, I don't think so. This is the evaluation theorem. This is how you evaluate this integral if you can find an antiderivative. So if I can find an antiderivative, I plug it in here at the endpoints, and that's the case, right? That's how I do it. As long as everything is nice, I can plug it in. The problem in the real world is you can never find an antiderivative. I mean, you think, like, again, the weather pattern, you just have antiderivatives, you just got to be smart enough to find? Of course not. I mean, the only way this can really work is replace this function by a Taylor polynomial. There's some error, but so what? You can make that error small. And then you can integrate a polynomial. That's not exactly it, but that's pretty much it. That's in reality. Now, we're going to spend a lot of time punching through all these formulas that I can make as painful for you as I want by throwing in gimmicks and tricks. And in reality, nobody cares. I don't, well, maybe somebody cares. I shouldn't be so condescending. I don't. What I care about is solving the initial value problem. And I'm going to use the technique of the tangent line or higher order or more advanced versions of that. That's how I'm going to solve the problem. All right? But I mean, knock yourself out integrating if you like. All right? So again, there are infinitely many of these antiderivatives, and we're going to spend a lot of time and a lot of pain doing this. I mean, that's why, everyone hates math, right? When that's not true. Again, this is the issue here, right? We focus on the pain. Why don't we focus on the things we can do? And it's not that hard, right? Calculating these tangent lines, global optimization on closed and bounded intervals. Because I need to make you suffer, right? That's it. But anyway, okay, I'm sarcasm. Okay, let's look at it. So now if I want to calculate, see, this is how I would calculate the value of the function. Suppose I want to go out, remember, x is any value here. Suppose I want to go from the beginning, 0, to some arbitrary but fixed point. It could be anything, a half, 2/3, whatever it is, something in between here, right? So if I do this, right, how do I do it? I can define an antiderivative. This is an antiderivative. I can calculate this value, right? I can calculate this value for any choice of A by the evaluation theorem or by Newton's method, the approach Newton used, right? And I can generate this function. It may be digital, a version, an approximation, but I can calculate this. So that gives me one antiderivative, right? One antiderivative. Now, okay, if I want to use this notation in general and make this look like a function, right? Again, x is a placeholder, right? This notation says x is a placeholder. X is any number along here. In this case, what I replace x with, x takes the value of a. But if I want to write this in standard function form, remember what the fundamental theorem promised you. There exists a function. Now, what we did with the tangent lines and the rectangles are effectively approximations. If we want to say there's a function, this generates it. Remember, we went from 0 to 1 before. This would generate it for any choice of x, right? So at a half, 1/3, 2/3, or at 0.3, whatever you want. This is in the function. It's the same thing, but this is in a function notation. And how would you calculate that? Well, you'd have to fix a particular a, right? 1/2, and then do your Riemann sums under here. But that's your function. You can say it's not very satisfying. No, I mean, you'd calculate it by using the tangent lines or, the rectangle Riemann sum method. But in principle, it is a function because this is a limit and I know it exists, right? So that's it. Oh, and so what I'm trying to point out here is, notice I keep saying x's here. It's not considered good technique to say if I went alpha to x, because it confuses what's the variable of the function, right? I want to see that x is the variable of the function. If I keep putting x's in here, yes, it's obvious to me that it's different things, but it just doesn't look good. So generally speaking, we replace this with what's called a dummy variable. You can call this anything you want. You could call it, capital X, fancy X, Y, chi is Greek X, right? I mean, you can replace it with anything you want, but it's just, if you're going to write it in this notation, right, this gives you the value of the function there, then generally speaking, you change it, right? It's just good practice. So this is it. This is the fundamental theorem, right? I have the function. I know that this function has an integral, is integrable. I give you the initial condition, right? So that's my fudge factor constant. This here is my antiderivative. Now, again, it's just theoretical. If I can't, again, and other than the easiest cases, I can't calculate this. So again, I can calculate this number to as accurate as I want using the tangent line method, which we do with time when there's only one derivative, or using the Riemann sum method, which you'll see I do by integration by parts and the Riemann sum method. This is what you're going to do. I mean, this is the key. This is the key. This is it. This is what you're going to do. And this function satisfies this initial value problem, the initial state and the dynamics. This function satisfies the initial value, and that's what I promised in the beginning. And I also told you how to construct it. Even though, other than the simplest cases, doesn't matter. I can construct this numerically to as accurate as I want. So I'm telling you the answer exists. This is it in practice. If I approximate this with tangent lines or Riemann sums, I know the smaller neighborhoods, right, more mesh points, a smaller mesh size, gives me a more accurate answer. How accurate do you need? And the advantage to that, whether I'm computing it using tangent lines or Riemann sums, this is trivial to do on, say, Excel. I mean, it's just any problem you're going to be able to do in ODE, I can generate a numerical solution. Nothing. Now, I'm not saying you wouldn't want to use those techniques, but today those are extreme problems. I mean, that's like InfoWars, right? I mean, this is like crazy town, put tinfoil on your head. I don't really mean it. I mean, there may be reasons for it, to be honest, but that's not what you're going to do most of the time. I mean, you may be a specialist, but this is the idea. I mean, in fact, my work, this is it. But I'm not saying nowhere, but this is it. So, I mean, the fundamental theorem tells us there's a unique solution. So this solution is one of these antiderivatives. And again, in the notation now, notice this is called the indefinite integral. And we'll come back to this later. And it's indefinite. Remember, the definite integral, right, had a lower and an upper bound, lower and upper, right? Lower and upper limit of integration is what it's called. Base times height, right? But the indefinite integral, well, you're not telling me where to start and stop. So it's not definite. It's not a number. I don't know. It's not definite. In fact, it's a set. It's a set of all possible solutions. So it's a set of all functions that meet the dynamics. Once I pick out the particular constant, I'll get the initial condition, right? That's my fudge factor. And that's a big deal. I mean, this is it, because this is the prototype of the kind of equations you're going to look at. Again, for whatever reason, the dynamics, conservation of mass, momentum, and energy, in the work I've been doing lately, the dynamics of the economy, you're given the derivative. You're told how things are changing. You can model that. You're told the initial state of the system and how things are changing. That's just the way it works. If it wasn't like that, it wouldn't work this wouldn't be the fundamental theorem. But that's how things are given to us. They're given in this prototype form, and that's why this is so important. Notice we're not given the function and want to find the derivative. I'll tell you where that comes from. It's just a knockoff of a cheap way. When I can't find the actual antiderivative, I'm going to guess. And the way I'm going to guess is I have to guess it, and then I have to check and see if I guess correctly by taking its derivative. Again, I don't think that this is certainly not the main use today. And bam, yes, I deserve that. Yes, you do. You followed this along, and good for you. Oh, boy, we're big mood. Okay, which method do you use? Tangent lines or Riemann sums? Well, you can do either. And I played around with the either or in some of my research, so I can see that. But if you're given it in a differential form, time, if your highest derivative is time, and this is exactly the problem you're going to spend most of your time with in engineering math, I'm going to use tangent lines because I naturally I have an initial point and the slope of the tangent line. So it's very natural just to use the tangent line approach. Again, if we could take time to do this, I did all those implicit differentiation problems by finding the derivative and an initial condition and just tangent lining it. I mean, it takes literally a minute. So if I'm given a derivative, I'm going to use the tangent line approach. If I'm given the integral form, integrals, I'm just going to use the Riemann sum, right? Base times height. Base times height, and sum them all up. And this is going to be important when we have spatial variables, And we're going to use integration by parts. We'll do that on the very last lesson. I'm not going to test you on it, but this is what you want to know. If you're doing structural mechanics, if you're doing fluid mechanics, you're doing heat transfer, bingo, this is your stuff. You're doing modeling the economy dynamically, bingo, this is your idea. Okay? So it just depends on your use. Right? Notice, you see this stuff all the time. Suppose you go to the lab and measure something. Here you go. I go to a lab and I measure it. I measure a point here. I measure a data point at 1/3. I measure a data point here. How can you? Okay, so I measured the velocity. I went to the lab and I literally measured the velocity at these points. Right? I measured the velocity. Well, let's extend it digitally by a constant, right? Well, once I have this, I can integrate to get that. That's what we did, right? I mean, you can use this stuff practically. It wouldn't exist. It wouldn't exist if you couldn't use it. See, I just hate it. You're beaten down, you're hazed by memorizing all these formulas. All these formulas for the inverse hyperbolic. Who cares? Right? All these algebra gimmicks, all these geometric formulas for related rate problems. We don't do it. We don't do it. You take these ideas and they're very powerful and they're very simple to employ. If they're not simple to employ, we don't use it. I'm not saying you can't develop these out in my own research. You push it, you do this and that. But on a practical level, I can solve any first order differential equation in a minute. Anyone by these techniques. This is it. So this is so powerful, and I just wish we could spend so much more time on this. All right. So point and slope, I have a tangent line, and there I have it. Now from an integral approach, again, compare and contrast. If I had the function, I didn't do that, I just did this crudely. But let's look at it. Suppose I have a function here, right? Now, what I can do is, if that's the derivative, I can put, right, digitalize it, right? I can do base times height under it, and I can get an approximation, right? Or what I can do is I can use a lot of rectangles, and you see how I get a better approximation, a better digitalized version of this, right? So I can get more accurate by taking a smaller mesh size. That's one approach. These are called H methods. This is what we typically do. We use piecewise constant for the derivative, which means the function itself will be approximated by piecewise linear, right? So these are H methods. I'm going to make the mesh smaller, right? So I have more rectangles, and I get a better approximation of the answer. That's one approach. Now this is interesting. What's another approach I can use? This is P methods. This is based on the concept of Taylor series. So if a linear approximation is this good, I could get a better approximation by increasing the order of the approximating polynomial. So instead of using the first order Taylor polynomial, which is a line, I'll use a higher order Taylor polynomial to approximate it. Now, again, the issue is pro and con. The advantage to this is if it's piecewise constant, the function is piecewise linear. So I only need one derivative. Once you start getting into Taylor polynomials, remember the pro and the con. The nice thing about a Taylor polynomial is you get the whole function out there, or at least the polynomial approximation to that function. In other words, I can write Taylor approximation equals, a polynomial. The disadvantage is I need higher order derivatives. I mean, suppose your problem only has one derivative. Right? Well, then you're stuck with what you can do. But that's the concept here. Now, again, this is the kind of advanced ideas we do. I can combine them. Instead of saying this is piecewise constant and the answer then is piecewise linear, how about if I say this is piecewise linear? You can see I get a better approximation, or piecewise quadratic. Right? So I'm going to start applying the idea of the Taylor approximation on each, right, on each H method. Right? I can combine these. And we do this. This is exactly what you do. I mean, again, when you see Riemann sums, it's piecewise constant. Trapezoidal method. I'm taking in the trapezoidal method this to be, instead of a constant, it's going to be linear on each of these. Right? You can see I get a better answer. And I can do Simpson's rule. piecewise quadratic. So on each of these, I'll do a quadratic function, right? In practice, these higher order integration rules don't matter. I mean, honestly, maybe in 1890, but I have a computer. Any of these one variable problems, I mean, I can just code this easier than I can looking up Simpson's rule, right? The time it takes me to look up Simpson's rule and apply it, I could just write the code on Excel and do it in less time. Now, again, in numerical calculations where you're doing trillions of these calculations, maybe there's some advantage. But I'll tell you the truth, I do these calculations, and I use piecewise constant. I do piecewise constant, as do most people 99% of the time. There has to be a particular reason why I don't choose piecewise constant, right? There has to be a reason why I don't do it. So if you were going to do a talk or a research paper and you came to me and you told me you're not doing a piecewise, I'd say, why? Justify the reason why. Why are you getting fancy? What do you gain by that? And often the answer is, I don't know. Somebody told me. Somebody else did it. So these are the ideas. I cannot begin to overemphasize how important the fundamental theorem of calculus is. It's the fundamental theorem of all of calculus. If you have any experience doing problems, this is what you're going to do, right? So this is everything you're going to do. I mean, again, I don't want to say, there are other examples, but they're the other types of things. That's extreme. Now, unfortunately, we're going to spend the rest of the semester not doing this. I'm going to do the rest of the semester hazing you. So we're going to do those extreme special cases because it makes you a better man. Even if you're a woman, it'll make you a better man. This is it. This is what has been ordained. And so, again, with this calculus course, I do have to hit the point so you can go on to Calc 2, 3, and engineering that. So we're going to spend the rest of the semester to the last day talking about how to apply basically the evaluation theorem. Okay, so good luck with that. I hope you get something out of it. This is the one. Okay, in all of calculus, this is the one lecture I hope you pay attention to. So good luck and have a happy tomorrow.